Welcome to the session on algebraic methods, proof by contradiction. The objectives for this session are to use proof by contradiction to prove statements. Let's begin by highlighting what a contradiction is firstly, and secondly, how to then carry out a proof by contradiction. So a contradiction is a disagreement between two statements. It implies that both statements cannot be true. Proof by contradiction is a very powerful method which is used as follows. Firstly, we assume the statement we wish to prove is false. Then, using logical steps, we show that this assumption leads to something impossible. It could either be a contradiction of the assumptions that we've made or a contradiction of known facts. And then finally, we conclude that the assumption that we must have made at this very start is incorrect, and therefore the original statement which we wish to prove is actually true. A statement asserting the falsehood of another statement is called the negation of that statement. Let's now take a look at an example. Prove by contradiction that there is no greatest even integer. Let's solve this. We're going to begin by assuming that there is a greatest even integer n. And in making this assumption, we have applied the first step. So we have assumed the statement we wish to prove is false. So let's continue with our proof. We're assuming that there is a greatest even number or integer n. In step 2, we're required to use logical steps to show this assumption leads to something impossible. So n can be actually written as n equals 2k for some integer k, because of course it's even. But if we add 2 to n, we obtain that n plus 2 equals 2k plus 2, which equals 2 times k plus 1. And of course that is even. So therefore, n plus 2 is even. However, n plus 2 is greater than n. Now this of course is problematic because in our original assumption we assume that there's a greatest even integer n. So there couldn't be an integer which is even greater and which was even. But of course that's been proved false, or we've arrived rather at a contradiction. This is where step 3 now comes in, and we can therefore conclude that the assumption is incorrect and our original statement which we wish to prove is actually true. So in our final line we can say, but n plus 2 is greater than n, which contradicts the assumption that n is the greatest even number. And therefore there is no greatest even number. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So this time we're required to prove by contradiction that if n squared is odd, then n must be odd. So let's solve this. We're going to apply the first step and assume that there exists a number n such that n squared is odd, but n is even. Now, n, because it's even, can be written as n equals 2k for some integer k. So if we square this, we obtain n squared equals 2k all squared, which is equal to 2 times 4k squared. In particular, the conclusion we've arrived at is that n squared is even. However, in our assumption, we had that n squared is odd. So this contradicts the assumption that n squared is odd. And therefore, our original assumption was incorrect. And the statement which we actually wish to prove is true. Therefore, if n squared is odd, then n must be odd. And now for example 3. Again, pause the video and have a go. Press play when you're ready to view the solutions. So we're required to prove by contradiction that if n squared is even, then n must be even. Let's solve this. Again, let's assume the statement we wish to prove is false. So we're going to assume that there exists a number n such that n squared is even, but n is odd. So, given this assumption, n can be written as n equals 2k plus 1 for some integer k. And therefore, n squared equals 2k plus 1 all squared. And this equals 4k squared plus 4k plus 1. We've simply expanded the brackets. This expression can be rewritten as 2 times 2k squared plus 2k plus 1. So in particular, what we're trying to say is that n squared is odd. However, this contradicts the assumption that n squared is even. And therefore, if n squared is even, then n must be even. Our original assumption was incorrect. Now let's take a look at another example. Prove by contradiction that root 2 is irrational. Let's solve this. We assume the statement we wish to prove is false. So we assume root 2 is rational. Therefore, root 2 equals a over b for some integers a and b where a and b have no common factors. If we square both sides, we obtain 2 equals a squared over b squared, and of course this implies that 2b squared equals a squared. And therefore a squared is even. But from example 3, we have that if a squared is even, then A must be even. Therefore, A can be written as A equals 2m for some integer m. And if we square A, we obtain A squared equals 4m squared. So therefore, A squared equals 2b squared equals 4m squared. And this implies that b squared equals 2m squared. But again, if we apply example 3, we know that if b squared is even, then b must be even. In other words, A and B are both even. Therefore, A and B have a common factor of 2. This contradicts our statement that A and B have no common factors. And therefore we must assume that our assumption was incorrect and that our original statement is true. Therefore, this assumption that root 2 is rational is incorrect. And so, root 2 is irrational. This brings us to the end of this session. If you have understood its contents, you should be able to use proof by contradiction to prove statements. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.